Okay. You know if I feel like that's a bit much. This one. Wait, can you turn it? Wait.
Yeah.
Yeah, there we go.
Okay. We good? All right, we're team 3.1, and we are doing a presentation on this paper sys bumps, which talks about speculative execution to break address-based layout randomization. Cool. So let's talk about the problem this paper is trying to solve. They're asking, okay, how can we use speculative execution to bypass this kernel address-based layout randomization, specifically for Mac OS running Apple Silicon? And we'll go through what each of these mean. First, what exactly is address-based layout randomization? I think we briefly talked about it in class when Professor Nader talked about the war in memory. But I guess the idea is, why do we want to have these random addresses? Surely that makes things harder if we need to randomize the addresses and figure out where we're accessing. Well, in fact, it's to prevent this class of attacks that use control flow hijacking, where you can reroute the program counter to run arbitrary code. Oftentimes, this is used to run code that spawns a shell, giving an attacker basically full control of your system. But there's a key limitation with control flow hijacking, and is that you need to know where you're actually going. So if you randomize your addresses such that the attacker doesn't know the address of the shell code or the gadgets that they need to run to spawn a shell, this effectively mitigates or stops this class of attacks. So I guess visually what that might look like is you have a bunch of programs in your memory. When they become randomized, each of them gets moved around in some way, but crucially, it's important to note that even though the programs themselves move around in your address space, within the programs, the memory is unchanged. Meaning that if you can figure out this offset between the start of your addressing space and where the kernel is for this paper, then you can determine the relative addresses of each of the parts of the kernel, and then at that point, basically, you've broken address space layout randomization. Because at that point, then you can determine the address of basically any arbitrary part of the kernel. Cool, so that's about KASLR. The second part is a review on transient execution. We're the first group, so it's maybe important to review. It starts with a branch. The branch, it might take a while to resolve the branch condition, so at the same time, it'll start speculatively executing instructions. Importantly, this often leaves a trace in the microarchitectural state. As we talked about in class, this tends to manifest in the cache. Eventually, this branch is resolved, and maybe at that point you have some results from your speculative instructions. But in the event that you have mispredicted this branch, you will discard the results from the speculation and also the speculative instructions themselves. But crucially, it leaves this trace in the microarchitectural state, and for this paper, that manifests in the TLB.
Well, so I'll go over the mic. Oh, the mic.
Actually, is it even? I don't know if my.
It's back.
Okay, so I'll go over the main contributions of the paper. We'll start off by talking about how are we actually going to find this base address. And we do so using basically a side channel attack, but on the TLB. And so it works basically the same way as a side channel attack, but in this case, we're targeting kernel addresses that will be shared on the TLB with the user space. So next slide. Yeah, so the first main contribution of the paper is that they had to reverse engineer this TLB. And so if you see this chart here on the left or on the right, basically the way they reverse engineered it is they targeted the TLB and they tried to call data for various numbers of ways and sets. And so for each way, they did W+1 so that they'll get a miss when the TLB fills up that number of ways. And so the actual structure of it is when they have a minimum number of ways and sets, the combined minimum. So in this case, it's 5 and 32 for way and set. And this table lists all of the different layers. If you can go to the next, yeah. So there's a L1 and L2, and it's split into data and instruction. And what they figured out is that only the instruction TLB is split. So there's kernel isolation on the user, on the instruction TLB, and that's actually to prevent those attacks that I showed earlier that breaks KSLR. Yeah. So this is a more basic form of that. So like just understand there's a L1 and L2, but they're both split like this. Next one. So if we want to, the main issue is that there's still a shared data TLB. So the paper tries to proposes an attack that would use a system call, and with a system call, they're able to load in a user argument or code into that. And so in this case, it's going to be loading in a kernel address into that system call. And normally, normally because we have this split TLB for the instructions, the system call is still going to check and do validation checks for the data TLB. And so we can't directly put like a kernel address into the system call. But there's still a workaround for that, and that would be the transient execution, right? Because the address is still going to be in the TLB and left in the TLB during that transient execution. Go ahead. Yeah, so the main way that sysbumps works is we're going to train on the speculative execution, get the speculation to mispredict, and then we're going to do prime and probe on the TLB cache. And with that, we'll be able to break KSLR and find the base address. So this is the pseudocode. So here, the first two sys calls are like training the speculation to mispredict, and then we do prime. We run the sys call with the actual kernel address. So this is where the transient execution is, and then we're going to probe during that time to get the kernel address.
And now we come to the evaluation methodology part. So they find out that you measure the latency. Here you can see if it's like a high and low, like a large range of this, that means it's an invalid kernel address. If it keeps keeping a high latency, that means it's a valid kernel address. And then they also recognize this small fraction of the high latency, that means it's the beginning of the data segment. And since the data segment offset is always constant throughout different processors, we can actually get to the end of the data segments, and that's where we find the kernel base address by using the end of this address minus the offsets here, and also the size of the data segment. And the main results they found is they use 1,000 attacks using different system calls, and they found out the accuracy and the time it takes to attack those processors. And turns out it's pretty high accuracy and a pretty low time to use. For the future works and follow-ups, so next slide. So the Apple actually acknowledged this and fixed this issue in the recent updates, but they didn't disclose what exactly they have done to solve that. But from what we have learned in the class, we know we can use the fence instruction to block and protect the system call. We can also restrict the speculative process. We can allocate the TLB entries for invalid address, so they cannot tell the difference between valid or invalid addresses. We can also further partition the DTLB, just like we did for the ITLB, between the user and the kernel space. For the future work, I think we can explore how we can use this knowledge on the kernel address to launch a more meaningful attacks. We can also try more complex side channels. And the reverse engineering they use in this paper can also be used on other processors, perhaps. And we can also explore other attacks using the structure of the TLB. And here is our discussion question, and let us know if you have any more questions.
Thank you all three. Do you have any questions for Edward, David, and Jamie?
Yeah.
Okay, I was wondering how effective was their attack in terms of the latency that it takes, because I think they are considering that you can tell me actually, do they consider that the randomization happens once, or it's like frequent you randomize the start of the kernel address?
They run these tests. So when Junyu was saying they ran this for 1,000 iterations, I believe it was like
It's
100.
7 tags in total, but it's like 10 attacks and 100 for
Yeah.
each tags attack.
It's like 100 boots.
Yeah, 100
So,
boots.
Uh-huh.
and this is just the average per boot, like per attack.
So there is no, it's not completely deterministic to find it. They should do multiple times in order
I
to
mean, it's
find the
never
randomized.
necessarily deterministic, right? But it's like you can tell from this accuracy, like
Yeah, 96%.
yeah, it's all quite high. So even if it like doesn't work the first time, then you can,
Try
reboot
it.
the computer and try
Yeah.
again.
Have you found any other work on other processors than M1 and 2?
Yeah, they try to use other processor, but it's really depends on the specific system calls. So seems like the system call they're using that version of the Apple processor didn't have that much of protection, so they can use that to access the kernel. But in other, they try it with like other like Linux and other companies' processor, and turns out it didn't work that well.
Okay, great. Thank you. Find some. Okay.
It says sharing not on. Okay. Where is it? I shared the wrong one. Okay. I think open it first and then come back to the share. Oh, wait, what?
And do I have to share the desktop? I think.
Yeah, just share the desktop.
Do I have to share?
Wait, what the heck?
Please listen to the second presentation.
Okay, so the paper we're presenting is called Downfall, Exploiting Speculative Data Gathering. So the main idea behind the paper is that there is a instruction in x86 systems called the gather instruction. And what it effectively does is that you can gather different memory locations into and then store it within your vector register file. So what the paper itself discovered with this instruction is that a very slow implementation would be once it passes through the pipeline, you just convert this instruction to multiple load or just multiple memory read operations. But then this is slow, for example, in the case where you have an interrupt, and then you have to restart your instruction from scratch. So what they discovered is that there is a what's called in the paper as SIMD register buffers inside the vector register file. And what this essentially is that it just preserves the data that's being gathered. So if in the case of an interrupt and then it's a non-filling interrupt, the instruction can continue from that point, just gathering the data from that buffer into your registers. And then what they also noticed that during speculation, if you have another instruction, that instruction can actually gather information from that buffer. So this is sort of where the vulnerability is at. So a simple example of what they gave was the gather data sampling instruction. So what your victim will do is that you'll just execute a gather instruction, and then when the victim executes that instruction, you're going to hope that the victim's data is inside a shared buffer. And then what your adversary can do is that you can just create a transient window, and then you can execute as the adversary, you execute the other instruction, and then hopefully you get the data that's within the buffer into your own register. And then you just try and move that data from the register to the cache using like a simple move or a simple load operation. And then you can use a cache side channel to sort of read that data. But interestingly, what they also noticed is that although that optimization is within the vector register file, it also extends to other affected instructions. So this also includes other SIMD vector read instructions, one of the SIMD vector write, vector write instructions. And interestingly, non-vector instructions are also vulnerable because they also use this optimization. So you have like fast memory copy instructions, like repeated moves, which repeatedly reads data from a specific location. And then these kinds of instructions also use that temporary data buffer as an optimization. So these are also other affected instructions. Yep.
All right, so then the paper went on to kind of talk about some of the uses of this attack that they discovered. So one of the big ones was they discovered that a lot of cryptography systems are actually very vulnerable. Specifically, they called out this one thing called AES new instruction. It's this instruction set extension that allows for hardware acceleration of AES encryption. And unfortunately, due to this attack that the authors discovered, this actually allows an attacker to access a victim system even if they're in completely separate VMs. So the attack methodology they used in the paper was they would have one VM running the AES encryption, and then the other VM would be using the gather attack to just basically eavesdrop on that and then discover the AES keys. This allowed them to get every single AES 128 key that they were looking for within 10 seconds, and they had a very high rate of success with AES 256 as well. Obviously, these are thought of as very secure and not defeatable cryptography systems. However, they did find that these are very vulnerable. The only knowledge that is necessary for an attacker to successfully execute this threat is that these systems must be running on the same physical CPU core, and they must be using SIMD memory reads. So the process it actually uses is the attacker prompts the victim to encrypt some random data using AES. During the AES encryption process, when this specific hardware acceleration method is used, the AES round keys will be loaded into the SIMD memory buffers, or the memory registers. So during that time, the second VM system can use the attack we've been talking about to actually look at these registers and process all this data. So due to the way AES encrypts, the round keys are actually loaded into this memory buffer and then taken out again multiple times. So the attacker just records every single bit of data that passes through the buffer, and then they use a frequency analysis to determine what are the most likely bytes that could be part of the key. Based on that, they can reconstruct the key and then test it to determine if they were correct. So what they found was this worked for pretty much everything. They did find that in certain cases, there would be too much noise to isolate the key, but they mentioned as a possible future work, they could come up with better noise reduction methods, or they could figure out how to run the attack multiple times or even longer in order to actually determine the key values. But arbitrary attacks on AES master keys, very fun. Okay, and the next attack they were talking about is with the gather data system. They basically the authors realized that this actually allowed for a very elaborate prefetching attack where data that was never accessed by any system or any software in the system could actually be accessed through the cache. So similar to the other papers today, this is about speculative prefetching. The novel part of this one is they found that actually instructions that function as a no-op, for example, this instruction here where it's a repeated move instruction, even if you say repeat this 0 times, which architecturally this is a no-op instruction, you're telling it to do absolutely nothing. This still allows the attacker to actually access 128 bytes of memory after the address where you're supposed to write to. So even though this is architecturally safe code, this is actually a very dangerous exploit because you can't fix this architecturally. This has to be some kind of hardware or software fix. So then the authors went on to go look at if this was a vulnerability that could be exploited in the Linux kernel, and the answer was yes. So as you may know, a lot of code traditionally relies on using stuff like memcopy, and then they have out-of-bounds checking and other stuff to ensure that attackers aren't able to easily access memory they shouldn't have access to. However, due to prefetching, the attacker can manipulate the memcopy instruction in such a way that the attacking system is able to see data that was never actually used in the cache. So they reported this as a CVE and are working with like the various companies involved to actually figure out how to fix this, because these instructions are on every single Intel CPU from like 2010 to now.
And also, the author mentioned another attack called get value injection attack, which is different from our previous attack. By doing so, first, the attacker will need to load in some index to the shared buffers like SIMD registers, and this index should be special. For example, it should be out of boundaries for the attacker itself, which means that the attacker cannot directly get access to that memory data, but it should be can be directly accessed by the victim here, so that the attacker want to steal that out of boundary memory data from the victim's access. Yeah. Then how can they do this? And after the attacker preload this index into the memories, the victim code will ask you the gather instructions here. So that by doing these gather instructions, victims will directly get access to the out of boundary memories into that locations here. So after doing this, the attacker can observe these memory locations by doing some side channel attacks like flush or reload attack to get the arbitrary data here. And here is the difference between the GDS attack and the GVI attack here. For the gather data sampling attack, the attacker do not need to run the gather instructions. Instead, the victims need to run the gather instructions. But for GDS, the attacker will run these gather instructions to steal the data from the victim. So and for the gather value injection attackers, the purpose of the attacker is to steal the out of boundary memory data, which can be accessed by the victim here. So this is two different kinds of attackers here. And the experiments of the paper showed that the gather value injection attack is much more difficult to do than the get data sampling attack. And also there are some mitigations and future works here. The paper mentioned that there are different kinds of mitigations you can do. First, we can disable SMT here, so that you cannot directly get the data, and you cannot share the data between these in the same mitigation, in the same memory or other registers here, but it will lead to a performance cost here. And also you can disable the gather instructions or disable the memory sharing during the whole process here. But all of these methods will cause a performance, low performance of these, all of these structures. And also for the future work, there are also two different directions. First direction is they will do a cross-vendor explorations. For example, they will test whether, because the current experiment only do on Intel SGS, but they can also test other CPUs like AMD or ARM architectures, which whether they have similar attackers or they are similar vulnerable due to these attackers. And also they can do tests whether other instructions except gathers like fetch or move is similar vulnerable during these executions here. And so the follow-up for the Intel is they add a microcode pass and they disable the get instructions from forwarding speculatively after the hearing about these attacks. But the question is, do you think is there any permanent solutions or any future solutions we can do for this? Because if by simply adding a microcode pass, it can prevent the gather instructions from doing this, but not the other instructions. Yeah.
Okay, thank you, Fan, Sun, and Kai. Do you have any questions for that? Do you have any solution for their question? Okay, I have a very small question. You mentioned fuzzing as one of the mitigation ways.
In the paper, what they mentioned was that prior to downfall, there was other, because Spectre and Meltdown has been a thing since 2017, 2018. There was a paper called the basic idea was that you would fuzz for instructions, so you check what instructions are vulnerable during speculative execution. Because prior to this paper, there was the LVI paper, which has the same idea, but the buffer, instead of being inside the register file, it's part of the cache instruction. So you have a write buffer within your cache. And then what they noticed was that that was also leaking. So and there are certain instructions that are vulnerable to that specific buffer.
Mm.
So you would try and create different, a set of check what instructions are vulnerable, and see what leaks. So that's what they mean by fuzzing. But then why they didn't find this instruction is because this is probably AVX 512 vector instructions. That paper only discussed the standard x86 ISA instructions. But when they used the tool to check for AVX instructions, they would found that that tool could identify downfall, which is this paper. So that's why they mentioned fuzzing as one of the possible solutions before you add more ISA instructions.
So is there any automatic way of detecting those vulnerable instructions? Or
I think it's just the same as like you just run it through a emulator and then see what kind of results you get from that microarchitecture emulator.
Thank you so much.
No worries.
Kevin William Young. Any of you is in the list?
So our paper is on computing with time, microarchitectural weird machines. So for a brief overview of the problem, well, modern CPUs tend to expose unintended side effects at the microarchitectural level, stuff among like the cache and the branch predictor, and these are exploitable by attackers. And microarchitectural weird machines enable arbitrary computation solely using these microarchitectural side effects. Traditional defenses analysis only monitor architectural states, so such computations would not be visible to standard tools, thus undermining malware detection, program analysis, and system isolation. And remember, transit execution attacks like Spectre and Meltdown exploit speculative execution to access restricted data during transit windows, and only architectural states will be rolled back after this prediction. And so microarchitecture machines use this thought process to take a step further beyond this leaking data and perform computations. How does one actually do this? Well, so entertain yourself and say that we have some sort of weird machine and we have weird registers and weird gates. So we have two types of weird registers for our inputs. We have instruction cache weird register and branch predictor weird register. For instruction cache weird register is a value of 1 if the instruction is cached, and value 0 if it's uncached, which corresponds to low latency, high latency actions. And for the branch predictor we register, we have a value of 1 if predict not taken. In practice, it's more so it should mean mispredict, but for the case of making pseudocode simple, we'll say not taken. And 0 if we do say taken. And the intuition is that, well, if we predict not taken, we can do speculative execution, in which case we can try to run some code while we have a transit window. So let's say you want to make an AND gate. What we could do is we could take the branch predictor and add some branch predict not taken and give us a transit window to check if our instruction cache is cached. Because if it's cached, then it's a low latency action to access the instruction, which gives us enough time left in the transit window to check if our output, in this case, a data cache, weird register, and then cache that value. And then the same thing with the data cache, if it's cached, and also be 1, just like the instruction cache. However, say that our instruction cache register doesn't have a cache instruction, there would be a high latency action to try to find that instruction, in which case by the time we've found that instruction, it's too late to now write to our data cache register, thus it's 0. An OR gate is a little more complicated. Instead of having 1 if statement, we actually chain 2 if statements. The first one is processed with a separate branch predictor that isn't our read register, but it always goes not taken, so it can effectively execute a bit of code with our instruction cache, in which case, since before, we check if it's cached, if it's uncached. And after that, runs the second if statement that simply just checks, did our branch predictor predict not taken or taken? If we predict not taken, we execute the code in that if branch. And the idea is if either if branch, for the first one, if the if branch had an instruction cache register with a cache instruction, we had enough time to write out some value to our data cache. And for the second one, if we predict not taken, then we just write to our data cache. As long as one of them worked out, then our data cache will have a cache instruction at value of 1. Now, you would think that with these gates, there's more gates that we could, that were made, but just assume that the other ones also work. Even if this is true, we still actually can't make weird circuits or combine these gates together to do complex logic, because reading and writing operations require a considerable amount of additional instructions. But more importantly, say you want to chain together multiple gates in series. Well, we don't have an infinite window of transit window, and we can't just perform speculative execution sequentially back to back to back. We have to hold some intermediate values at the architecture level between transit windows, which defeats the entire purpose of what we're trying to do. Because at points we're trying to run it at the micro architectural level and hide stuff from the register.
So using these word gates as a basis, the whole idea is we want to create a larger computational circuit. And in order to do that, just as Will mentioned, we need 2 properties. So firstly, these individual weird gates, these operations are contiguous. So activating one and in sequence, they should not affect each other's behavior. So they should be independent operations. And the second one is that transferring values between these registers must happen. So we need to transfer data between input and output registers in order to maintain this data flow. However, with that, there comes a lot of limitations, just as Will said before. So the first big issue is that with consequent activations, we require mispredictions in order to create that speculative window that the weird gates need to execute. And if we want to continuously have the branch predictor mispredict, that means we need to train it to mispredict, but it also comes an issue because of branch predictor unit improvements. So with global and even local history, as they improve, we're going to mispredict less and less. And the more they predict right, it's going to expose our traces, since it's going to force the weird gate code to execute speculatively, they're going to execute non-speculatively, which means it's more exposed. The second issue of value transferring is that we want to transfer between different types of entities. So that means that we want to transfer between, maybe we have a data cache word register, and we want to transfer that value into a different type of entity. So like a branch predictor word register, not the same type of entity. However, that has a large issue, because if we want to transfer across two types of entities, that requires a lot of architectural operations. So for example, if we want to transfer a DC word register to a BP word register, that's going to require training this CPU, maybe do like a continuous loop or like timing measurements in order to figure out like the cache residency. Both of those operations are architectural, and which means that they're very exposed in the traces. However, in order to mitigate this, we want to transfer between similar entities. So like a data cache register, data cache register. So here's some pseudocode of how it works. So we would create a speculative window by creating an abort somehow. So in this case, we want to divide by 0. And by creating that speculative window, then we can execute these instructions in that window. And what happens here is D0 is a word register, and we want to transfer that value to D3. So if D0 is cached, so D0 has a value of 1, then it's going to automatically cache D3 because the address call caches D3. So essentially, D3 is going to get the value of 1 if D0 is 1. If D0 is 0, so it's not cached, this creates a stall that extends further than the speculative window, forcing D3 to never get cached. So D3 indirectly gets value 0, which you can see how D3 gets assigned the value of D0 essentially. And by combining these two statements together, we can form an AND gate here or an OR gate, sorry. Because if either D0 or D1 is cached, it's going to cache D3 before the window. And similarly, you can see if we had all these in the same state or statement, D2 will only get cached if D0 and D1 get cached. If either of them are not cached, it's going to stall, which prevents D2. This creates that AND OR gate that we were talking about. And this essentially forms a larger combinational circuit because after we create a transactional window because in the paper they use this thing called TSX technology. So these X begin statements and X end statements. These X begin and X end statements, they create an isolated execution window, and that's important because it sort of hides computation. And the biggest thing about it is they can abort transactions without using constant mispredictions to create speculative windows. So that's divide by zero fault. There's also other commands such as X abort that create essentially the misprediction window and allow you to execute code. So now by doing that, right here, if we measure the timing measurements, we can essentially move the registers. Great.
Definitely.
So unlucky. What are you gonna do?
We can connect through the PC.
Do you have HDMI?
On mine, yeah.
Yeah, just plug the computer straight in. Or, but then it won't be on the. No, it'll still be on Zoom, right?
Yeah,
Yeah.
that's fine.
Or the,
Here.
Do you want to move your?
No, it's on this end.
I think it's the system. Maybe we, let me just change the source.
That sucks. Can you join the Zoom from there?
Yeah.
Perfect.
Yes. You should contact.
For us.
Yeah, but.
tired.
I sent a message on my kid. I'm pretty sure.
Well, let's see.
The one plus the, I have to send myself. Yeah. Right, especially since it's online.
Would you put 9?
Where's the
Oh, yeah, I have it.
Where's the keyboard?
976
Uh-huh.
6701 4693 4693.
Okay, got it. Thank you.
Yeah.
I'll see you.
High school?
Yeah, 236.
76?
It looks like you're showing a picture. I was actually looking at that one too.
But
yeah, I think I decided.
Yeah, I see. Yeah. No, I like it. Yeah.
No, when I saw L, that's what was like, oh my God.
That's such a really
Recording in progress.
Good.
Well, you just do the first part.
Nice.
Like, he's literally ready for it. He's replacing all the same time. He's like big processor.
Sorry for this. Would you?
Okay, so anyway, what happens is, okay, we have these execution windows, and now these are happening in the microarchitectural state. So what we can do in the architectural state is we measure using cache residency operations to measure the time. So here we measure D2, and if the time that we think to access, if it's under the threshold, so basically if it's cached, then we know that it's cached, and this is going to result in 1. If it's not cached, then it's going to be greater than time threshold, and it's going to result in 0. So essentially, in the architectural state, we can transfer these values from the microarchitectural state to the architectural registers. And this is important because that means that in the architectural visible state, we only see timing measurements and not really the computational side, which hides a lot of that computation to make it less efficient. However, these timing measurements have some variability because of system noise. Since we're measuring time, anything can affect it. However, they said that the gate inaccuracies are very minimal, so it's still relatively pretty reliable.
Yeah, so what are some applications, or what can we use this for? So the first one that the paper talks about is a obfuscation system, which is just like hidden malware or a hidden program of anything that you want to do on the computer. So you have an encrypted payload that is like what you want to execute. It could be like a reverse shell. It could be something to exfiltrate a password, something like that. And then you also have an AES key and a jump to that encrypted payload that you put on the machine behind one of these transient windows. And then you ping it continuously with a code. And then when the correct ping is received, we use the weird circuits to XOR with the jump and the AES key, revealing the jump and then revealing the key. And then the encrypted payload is then decrypted and then jumped to with the revealed jump. And so that kind of code block is seen in this image. But this is able to be executed without someone with full permissions who is able to scan the code and run it on their own, being able to see like what's going on because the payload's encrypted, and then the jump and key are only visible after going through the weird gates, which is only happening at the microarchitectural level. And then this can also be used for kind of general computations. The example they give is a complex hashing function, SHA-1. And this is shown because it's difficult because if anything messes up, then your hash is going to be completely different than what you expect. And so since our weird gates and weird circuits aren't 100% accurate, the paper uses a way where they repeat each gate and then kind of use a voting system to determine what the actual computation is. And so there's kind of a couple parameters that they talk about in the paper that they varied, and they found some optimal parameters that give good accuracy over good timing. And then their evaluation methodology. So they create this library Skelly, which kind of references those different parameters that they can use and to implement a bunch of different gates, AND gates, OR gates, XOR gates, so they have a full complement and can do any computation. And then they evaluated kind of the accuracy of these gates and the delay of these gates. And then they talk about the weird obfuscation circuits and how they were able to create a reverse shell and exfiltrate passwords without being detected. And then we have some discussion questions, and if you guys have any questions for us.
Okay, thank you so much. Any questions?
Do you remember some of the parameters that you mentioned, like the SKNs?
Yeah.
Like, what were they kind of looking at with KP performance?
They gave one example, and I think it was like 3, 5, and 10 or something like that. But like they didn't like go through like what all their trials were. They just spit out the end result and said this is the one we used.
Okay.
Which was kind of interesting.
I think also they said they didn't try to like once they got to like their most improved parameters, they didn't try it any harder. I think.
Yeah.
Okay, got it.
It seemed like they didn't like do too much optimization, but they were showing that like you could do optimization if you wanted to balance like being accurate all the time or like going fast and not being accurate.
Got it. Thank you.
Yeah.
We have one more.
Yeah, so they actually mentioned your paper in our paper. It's the one that's next.
Oh shit.
They, basically, so TSX is like no longer supported by Intel. It's disabled by default. So I'm curious if like in this paper they mentioned any follow up to like how this could work without that, or if anything like extra.
Nah, their entire thing was they were reliant on like the board technology that TSX has, because that's the whole point of not using that BPU. But I guess that's good to know for them.
Yeah, there's like a little paragraph on it. I don't know if you.
Maybe the same research group have done a similar work after we.
Yeah, I'm actually not sure if there's commonalities in the authors, but I could check later.
That would be great. Thank you.
Yeah, thank you.
Okay, it's almost 3. I think we can have a 10-minute break, and then we can have 3 more presentations on the second half.
I don't think any of them are.
Okay. Yes, please.
Okay, so the paper that we did was the gates of time, improving cache attacks with transient execution. So the central problem addressed in this paper is how to perform cache attack.
Oh, Go back to HTML. Would you give me that cable, please? Thank you.
This way.
Okay.
Okay, I'll be careful.
Yeah, I think we just don't touch that.
Okay.
Don't
That
move.
cable, you cannot get out of here.
Yeah, you can stand here.
Turn it off.
Maybe if we do
Little weak is out of all these.
I can connect that one to my laptop.
Your presentation, it's finished. And you went over time again. Yeah, it's hard to write.
Wait, you're like mega connecting it.
What? Yeah, it wasn't. Yeah. Some of the voltages were lower case and some voltages were empty.
You're still
Oh, it's still recording.
Just give us the full score.
It was like some of the paper, which is built on.
It seems that one is off.
Yeah.
You has to see it.
Oh, video. Yeah. Oh wait, did I do it? That's my bad.
Those are just buttons.
No, I think the projector itself is just turned off. No, this one's on.
Yeah.
Is there a button that turns off and on the projector?
I think
We tried that
pressed
one.
it, and it didn't work.
Is there another one? What if we tried it like
What if you tried pressing and holding? Turning it off and on. I'm a computer science master student. I think I can figure this.
You have to just turn it off.
No, but we don't have we cannot turn that one off.
I don't even think that one's. Oh, I think it's turning back on. It's turning green.
Oh, it's on, it's on.
Okay, just don't go away, touch anything. Nobody knows.
Fingers crossed.
Okay, I'm seeing a
Do
light.
the PC again?
PC.
It's starting up. I see light again. Oh, okay.
Oh, you tapped it and it came back on. That must have been it.
Yeah, screen.
Yeah, it's touch screen. Yeah, and the teacher would have to recalibrate.
Yeah, I thought the
Yeah,
calibration
the
was so
calibration
fun.
Oh,
Yeah.
yay.
I think we can start over.
Yeah.
Okay, we'll start over. Okay.
Hi everyone. Take two. So our paper is The Gates of Times, which is improving cache attacks with transient execution. So starting off with the problem, the central problem addressed in this paper is how to perform cache attacks in restricted environments, particularly where high resolution timers are not available. So traditionally, cache attacks rely on accurately measuring small timing differences between cache hits and misses, which becomes hard in environments like modern web browsers that restrict access to fine-grained timers. While there has been extensive research on using speculative execution to extract sensitive data from memory, this paper essentially asks, can speculative or transient execution be used to improve cache attacks themselves? So moving on to the problem background, to understand the context of this problem, we need to look at two key concepts, which are cache-based side channels and transient execution. First, cache attacks like flush reload or prime probe exploit the fact that accessing data from the cache is significantly faster than accessing it from memory. By observing these timing differences, an attacker can infer what data a victim process accessed. However, the accuracy of these attacks heavily depends on the availability and precise timing measurements. So moving on to gates, the slide focuses on the core innovation of the paper, which is essentially using speculative execution to build logic gates that operate entirely through changes in cache state. So in this model, a memory line that is cached is treated as a logical 1, and while an uncached line is treated as a 0. These logical values are manipulated by transient instructions that may or may not execute depending on branch prediction. So for example, the NOT gate, which is shown on the bottom right, is implemented by speculatively accessing an output address only if the input address is not cached. So in the presence or absence of the output address in the cache, this tells us the results. The authors built a variety of gates using this approach, including NOT, NAND, NOR, and buffer gates, and demonstrated that these gates are also functional across multiple processor architectures. So two styles of the gate design are explored, one that relies on branch training and one that avoids training by using fixed control flow structures. And the trade-off between these two are just accuracy and speed. And then moving on to circuits. So after building these individual gates, the authors demonstrate that these can be composed into full circuits capable of meaningful computation. They built three significant examples of 4-bit ALU to perform basic arithmetic around the SHA-1 cryptographic hash function and a simulation of Conway's game of life over a 12x12 grid. These examples not only show the computational power of the gates, but also serve as a practical proof of the Turing completeness. They did this because it's not always 100% accurate. For example, executing the ALU's 250 gates of the circuit produces the correct result about 80% of the time.
Okay, so they kind of explain two separate attacks in this paper. Both have a pretty similar threat model, assuming the attacker can execute arbitrary user space code on the same physical machine as the victim, but that they can't observe the victim process directly, just like most, cache side channel attacks. The first attack focused on building eviction sets in WebAssembly using, like as mentioned, low resolution timers only, since that's the only timers you have access to when using JavaScript. And things like that. And the second attack focused on attempting to sample the cache state at a rate higher than the clock rate, so facilitating fast attacks with slow clocks. And I'll talk about them in order. So the first one, kind of a step-by-step. What the authors did, first thing was basically just implementing the transient execution logic gates in WebAssembly, like how Shruti described. And the second was essentially the problem with these sorts of attacks in WebAssembly is you only have access to low resolution timers, so you don't have super fine granularity. So they wanted to amplify the cache state using a hierarchy tree structure. So basically, what that implies is instead of just having a single modification affect a single output, they kind of changed it such that the input to one of these gates would then affect kind of cascade down the tree structure. So in order to determine if the address is or is not in the cache, instead of just checking one address, you kind of cascade your way fully down the tree and basically just make operations take longer, essentially. So by integrating hypertree amplification into existing eviction algorithms, they don't talk about the algorithms themselves in detail in the paper, they're able to kind of measure access time using the low resolution timer by just increasing the length of the access time itself to identify the amplified timing differences. And then basically constructing and validating eviction sets and optimizing iteratively, we'll talk about in the next slide, which is the evaluation. So if you want to...
Sorry. So in order to basically just prove that their stuff worked, they ran 1,000 runs. This one is not the WebAssembly one. There is another one. The WebAssembly one, the hypertree is not as involved, so the differences were not as big. So that's why I picked this picture instead. So here, basically, you take your root address, like cache, hit or miss, and then it gets blown up into all these other things, which makes it more easily detectable. And then you do 500 runs with the root address. They care about cache versus not. And then here on this chart on the right, you can see that the time between those two is significantly different, over 100, 200 milliseconds. And they did like a statistical t-test as well to say like, okay, these are statistically far enough apart that our claims are accurate. But I feel like from the graph, it's pretty clear. And then they basically did the same thing on WebAssembly, and because their hypertree was not as involved, the differences are smaller but still notable through the same statistical t-test.
Yeah, so for the eviction set creation, that's the second part of the attack. So they evaluated 100 different runs basically, and in those runs they found the eviction set 78% of the time and stated that the failed runs were due to excessive noise. So basically, if other things are happening in the cache, anything that has to do with transient execution, like these gates are like provably not necessarily deterministic. You're not going to get accurate results 100% of the time. Hence why some of their runs failed. According to them, kind of when they reran these failed runs, they were able to find an eviction set, but essentially none of these attacks come with like a 100% like guarantee every time. But they are like statistically possible to make happen. The second attack is just a variant on prime and probe. They call it prime and store. Essentially the way that this works, they have this generic version and then also an example. So the prime step is pretty much the same as like any regular prime and probe attack. They repair the cache by loading the eviction set. And then in probing, basically what they do slightly differently is they use one of their NAND gates to repeatedly probe the cache set, and then basically place the outcomes of each probe in separate unrelated addresses to check later. So they basically split up the probing step and then the timing step into two separate things. So they do the timing step next, or the testing step next, basically testing each output address by, after sampling everything, placing them all in separate unrelated addresses to determine the output of the gate. Basically, they do all of this post-sampling to avoid any interference during the actual sampling process. And then kind of analyzing the timing data to attempt to infer whatever they want to infer about the victim memory access patterns. The specific example they talk about is related to like the L12 crypto system. So basically focusing on the square optimization on the modular explanation routine. They used a form of that that's like provably vulnerable to cache side channel attacks. And yeah, probing, they basically probed when the victim performed algorithm decryption and then interpreted the timing data to attempt to infer the sequence of square and multiply operations performed during decryption and to reconstruct the secret exponent of the modular explanation routine based on that sequence.
So in order to make sure that their example worked, they spent like 10 hours getting 100,000 different traces. I think like 1% of those weren't like failed, so they threw those out. And then from there, they also filter out like trace errors that are observable through a bunch of consecutive square operations. Like I think 11 of them in a row. They're like, oh, that's probably a trace error. Let's throw that one out. And that occurred maybe 1 in 5 times. They then took the remaining traces and then compared those against like the ground truth. This chart represents the frequency of ones that closely match the ground truth. So you can see that they have a pretty good coverage of all the different like spread over the locations. And then in order to just show that the attack actually works, they take all of the segments that closely match, or like they take a variety of existing segments, I think 22,000 of the 80 something thousand that they're left with after all the various filtering. I think that more than that amount had 0, 1, or 2 differences from the ground truth. And then they merged them using their stitching algorithm to fully recreate the key after like basically 15 minutes. Additionally, we found some other papers that cited this work. This first paper is like the same thing, but for Apple Silicon. The second paper expands on the work in this paper to create a new attack called evict spec time, which in addition to just determining like if something has been accessed, it also can tell you when. And then the paper also mentions this third paper, optimization and amplification of cache side channel attacks, as another work that's done by David Kaplan, I believe. And they take advantage of return address prediction to also do amplification, I think, of around 600 milliseconds, if I'm remembering correctly, but a pretty significant margin.
Yeah, I just wanted to add one last thing on eye leakage that I thought about when we were looking at the previous paper presentation. Basically, these gates they mentioned they work pretty well on AMD processors, like Intel processors, and also like this was test based on ARM. And I think the reason they're able to do that is they don't use any like special constructs like the previous paper used Intel TSX as kind of like their like linchpin in allowing the gates to actually work. But since this paper relies basically on just base system operations, they're able to, with relatively little change, port them to other architectures and have them work decently. So these are the main discussion points. And then if you guys have any questions, please let us know. Thank you.
Thank you, all three of you. Do you have any questions for that? Nothing. I have a very small question. When they published this?
23.
23. So it was like 2 years after the previous paper, or the paper that they talked about.
And somebody mentioned that they construct the key after 14.30 seconds, like 40 minutes or something. That's been the entire attack from like constructing the eviction set all the way to tracing the cache.
The trace took like 10 hours before that to get all the like 100,000 traces that they worked with. I don't think they fully used all of them, but they just gathered a wealth of them prior to merging to recreate the full key. But
so during that 10 hours, the program was running and doing the algorithm encryption. That's what that means.
I think so. They also have what's nice. They had like a nice appendix as well, where I'm not going to leave this, but where they kind of describe everything. They published all their code on GitHub for recreating the attacks. I will say, like for the algorithm attack, I'm not sure how practical it is in the real world, both because like of the time it takes, as you mentioned, but also because algorithm itself is like CCA2 insecure, so it's not like necessarily the most practical crypto system to be using if you want like full security under like a really complex threat model. So.
Yeah, that's another story, but
yeah, I don't know.
Thank you. You, Charles, and Jason. And maybe Johnson. Are there three people? Did you get? No, but I gave you the access, right? You have.
Yeah. Just 1 second. Turns out our first page is missing.
No problem. It's working?
Yeah, it's working.
Which
which one are we going to use to press the project?
You should share a screen.
Oh, share screen. Okay.
On Zoom.
So hello everyone, today we're going to have a presentation on the page walk side channels. My name is Jason.
My name is Junse.
My name is Michelle.
So first of all, we need to know that how CPUs optimize performance. The more the CPU doesn't just follow code, they just guess what's coming. So the first was the branch prediction. We covered that a lot in the lecture. For cache, if there's someone watching, they will see the path that you thought it would take. Then the speculative execution. For a line like line close reference pointer. Your reference pointer, the CPU might guess the pointer is valid and start accessing memory. Even if it turns out to be wrong, the cache was changed, and the attacker can observe whatever it's in the cache. And we have the data memory prefetcher. It preloads the data that looks like a pointer target, even if the code never uses it. This also leaves footprints on the cache. Think of the CPU as a delivery driver. Even with an invalid address, it checks every layer of the route. Like it checks something like the street, the city, and the attacker watching can figure out the direction where the cache was heading to. Next slide, please. So in an x86 system, every virtual address is translated through 4 level page tables. Each level from PL4 down to PL1 use 9 bits of the virtual address. Every lookup involves memory access, which touches the CPU cache. And that's where the side channel attacks begin. It's like searching a set of paper maps. Even if you never reach the destination, someone listening can hear that how many pages you have flipped, so it can infer where you're going. Next slide, please. And we also need to know the difference between the traditional attack and the page walk side channel. For traditional attacks, it likes the prime and probe. It only leaks from like 6 to 11 bits of the address. They only work if the secret is a valid and then valid address. But PWSC is not different. It's not the same. It changed everything because even for an invalid address, the CPU still walks the page tables, and each level leaves a trace in the cache. And by following these footprints, the attacker can recover up to 42 bits of the virtual address. This is a massive improvement. It means the attackers can now piece together almost the entire memory address, giving them far more precise access to the sensitive data. Next slide, please. So how the secret trail captured? First, the attacker flushed the TLB and the page walk cache. This ensures that the CPU must go through a full page walk. And then it primed the L1 cache, filling each set with known patterns. Next to it, the system triggers the victim to dereference the secret. And finally, the attackers probe the cache to see which sets got evicted. But here's a challenge. There's going to be a lot of noise. The system background page. When the system background page walks, there will be some unrelated memory access. So the attacker used the differential prime and probe. They run the whole process twice, once with secret access, once without. Subtracting the results filters out the system noise, isolating only the change caused by the secrets. And that's how PWSC sees what else no one else can.
So let's talk about the PWSC order oracle. So the key idea here is that the PWSC is a cache side channel that lets an attacker see which cache sites are touched during the page walk that depends on some secret. So this by itself sounds useful, but the issue is that the attacker can't tell what a single cache hit actually means. So like whether it comes from the level 4 or level 2 of the page table. So we need to figure out which cache site correspond to each stage of the page walk. So to get the useful information from the hits, with the attacker needs something we call a order oracle. So its job is to help the match each cache access to the correct page table level. So instead of a bunch of random cache hits, you get a clear picture. So without this information, it's just noise, and you can't figure out like the secret behind the accesses. So let's see how attacker figures out the page table level using the order oracle. So first is the memory mapping order oracle. Here, the attacker sets up the dummy memory in a way that the page walk only goes down one level at a time. So each step reviews one page table level. And on the top of that, they brute force the lower 3 bits of the index to see the exact match, kind of like narrowing down a log combination. And this approach is pretty useful. It led an attacker to leak up about 42 bits of the secrets. And the second one is the page walk cache oracle. This one is a bit different. It doesn't mess with the memory mappings, but instead it flashes the certain interest in the page walker's cache. That way, the attacker gets to decide which page table level the MMU looks up next. So it's cleaner, but it doesn't need the brute force. But it just leaks fewer bits. About 30 bits max, and mostly high order BPM bits and part of the offset. So it's kind of like the trade-off: more bits means more work, and fewer bits means simpler approach. And also the paper also mentioned the case study one, which is combine the PWSC with the Spectre PHI, which is basically to a trick to get the CPU to speculatively run some sensitive kernel code. And this makes the CPU touch secret data in the memory. And then PWSC picks up the cache traces that reveal reveal that secret was. When the Intel SLAM feature is enabled, the attack gets super powerful. So they have this sliding window that can bypass the canonical address check. And the attacker can pretty much leak about 99% of the entire physical memory. They actually showed it working by pulling out the root password hashes and readable XE text with over 99% of accuracy. And even for more complex non-XE data, it still leak over about 82%. And now, even without the LAM, the attack still works, just with a little more effort. They tested under the post-quantum crypto system. By leaking just a subset of the coefficient used in signature, they can recover the full secret key in about 3 hours total. That's about 150 minutes leakage plus 81 minutes to finish the key recovery.
Now let's switch gears and look at another type of attack that the paper mentioned. When we combine Intel's DMP with PWSC, we get a new way to leak secrets. This leakage can even be done from completely invalid pointers using just microarchitectural behavior that doesn't require any memory permission. It's all started with reverse engineering Intel's DMP. And Intel's DMP is very easy to trigger. A simple loop over a pointer array trains it, just as bottom right graph shows. Then just a single memory load can activate it again, as long as it has a matching PC pattern, and no dereferencing is needed for that load. And the matching is very loose. Only the lowest 10 bits of the PC matter, and the DMP speculatively dereference data 128 bytes ahead, which make it easy to predict and manipulate. Now here's where PWSC gets involved. After training the DMP with the streaming access pattern, the attacker can trigger it with just a simple load. That load causes DMP to speculatively dereference a pointer that points to a secret value, even if that pointer is invalid. This speculative reference triggers a page walk, and PWSC detects which page table entries are accessed by monitoring their cache effects. Using a memory mapping strategy, the attacker figures out which level each access came from, and from that, reconstructs up to 42 bits of secrets virtual address. They put this attack to test against the ERIM, which is Intel's MPK intra-process sandbox. The attacker trains the DMP outside the sandbox and then triggers it inside. And PWSC observes the leak. No permissions are violated, but over 42,000 bits of data are extracted with a very high accuracy of 82%. This breaks the isolation guarantees we usually trust in sandboxing. And since this attack is triggered by Intel's DMP and PWSC, guys may wonder if we use Apple's DMP and PWSC, does that still work? And the answer is no, Apple's fine. And there are some defenses for both the case studies. For the case study one that Junze just introduced, we have Spectre and Spectre and last. Sorry, there's a typo. We have Spectre and last, but it turns out that there has only limited protection for that. And for my case, we have Intel's DOIT and IPPP to disable the DMP, but it's not accessible to normal software. We think that the paper shows combining speculative CPU features like DMP with a new side channel PWSC can leak data across isolation boundaries, even without real memory access. We realize that how dangerous these hidden behaviors are. Just the way the CPU speculates and walks memory can expose secrets. We think that future CPU designs need built-in protections to stop features like DMP and PWSC from leaking data behind the scenes. And we have 2 discussion questions for you guys. Thank you for listening to our presentation.
Thank you. Do you have any questions for that?
You mentioned earlier that Apple was safe. Why is that?
Because the paper just wrote like that, and they said that there are, I don't know what this corporates like GoFetch or something that they monitor and measure Apple's DMP, and they said that they're fine.
Okay. And also they have like a random page table access. So it's like you set up just determinism mapped. Yeah, they have like randomized how the hypertext map to the cache.
Got it. Thank you.
Thank you. Last group, Vincent and Jacob.
Oh, wait. I have to enter slideshow first and then share it. No. What the heck? Yes. There we go. Oh, wait. Okay, there we go. All right, sure. All right, hello everyone. We're going to be presenting the paper, GoFetch, breaking constant time cryptographic implementations using data memory dependent prefetchers. I'm Vincent.
I'm Jacob.
We're group 3.6, by the way. Okay, so the previous group already introduced data memory dependent prefetchers, but we'll just bring it up again briefly for our problem. So DMPs, they preemptively, because they're prefetchers, right? They dereference cache data that may resemble a pointer, whereas they kind of treat data as addresses. Now, this is a problem because attackers can then prepare pointers in input to the victim program, observe if the DMP dereferences them, and they can use this with the traditional cache side channel attacks we learned in class, right? Like using techniques like prime and probe to just check cache latency to see if the DMP activated. And they can do this to kind of deduce properties about some kind of secret. This is a problem because although many state-of-the-art cryptographic software use like constant time programming, they're still actually vulnerable to this new avenue of information leakage, because although like the algorithm may not depend on the secret directly, like in terms of like the time executed, whether or not they activate the DMP might still depend on the cryptographic secret, and the attackers can use this to kind of deduce information about the secret, which is what this paper is about, right? So a little bit of background on why DMP can leak information. Principally, it's because
whether or not the DMP activates, and if it depends on the secret or not, like whether it activates, kind of leaks properties about this key, right? So if we consider this example, right? If you consider any cryptographic implementation, you kind of have to have a step where you're mixing kind of the cryptographic secret, so like S, for example, and an attacker-controlled input. So like say like the ciphertext, for example. This XOR is a stand-in for like, you can think of it as any arbitrary cryptographic function. And then whether or not the DMP activates on this kind of intermediate value y, like when it's loaded from memory, whether or not this activates determines if the pointers are like dereferenced, and that causes like data to be brought into cache, right? And then from there, you can kind of just use your traditional prime and probe that we learned in lecture to use a cache latency to then deduce whether or not this DMP activation happened, which allows you to deduce control flow about the program and ultimately some property about the secret. Before we jump into the contributions, just a little bit of background to the threat model that this paper deals with. It's mostly a pretty practical and realistic setting. The main points is just that the attacker and victim are co-located, so they're on the same machine, which is a pretty typical setup. The attacker only runs unprivileged code. They don't actually need to run any privileged instructions for this attack to work. All they need to do is be able to monitor cache latency, because that's what tells them whether or not DMP activates or not, and what ultimately enables this attack.
Yeah, so one of the main contributions of this paper, there's 3, and one of the main ones is that they actually reverse engineer the DMPs on the Apple Silicon, I think M1. So what they find here is also building off previous work, is they find that every time there's a fresh L1 fill, the DMP will be activated on the data brought into the L1. So it scans all the 8-byte words in the 64-byte cache line, and treats them as candidate addresses. So it looks at them and thinks that they might be addresses, and it dereferences all of them, and then issues a load to bring into the cache for all the addresses that are in that original cache block. And if there's several pointers in that cache line, it'll actually prefetch all of the pointers in the cache line. And it works. And what they found is that previous work did not, is that it also works like even when it's not just pointers, but there's like, let's say a pointer in the cache line, and there's some dummy data and also another pointer, it'll still prefetch both pointers, which is novel for this work. So there's a couple restrictions on this I won't go too deep into, but basically it needs to be a fresh L1 fill, like it can't already be in the cache. The pointer and the actual pointer's address need to be in the same 4-gigabyte region. There's also like a small history filter to make sure the same thing isn't prefetched twice in too short of a time. Obviously, the line must be absent, so it can't already be in the cache, and also needs to be a valid 8-byte form. So basically, if it looks like a pointer and it hasn't been prefetched recently, it will be prefetched. The DMP will activate. So this is the main like baseline example of a situation where the DMP can be exploited with a side channel attack. So we see on the right, there's this CT swap function. And so basically this is running on the victim, and the attacker will send this victim A and B arrays. And then eventually the victim will need to run the CT swap in its own process to do some sort of, function. And whether it swaps or not is based off this secret that the victim has, right? So what happens here is in this function is that basically the contents of the A and B array will be swapped if the secret is true. And this is internal to the victim. This is just an example of a situation where this could be exploited. So the attack works like this. So the attacker fills the B pointer that they pass, the B array, with a pointer address that they know ahead of time, right? And they fill the A array with a bunch of dummy data. And so they pass this to the victim, and the victim eventually will run this CT swap using this A and B. So normally, this swap is actually a constant time because they use this XOR trick where it doesn't matter if you're swapping or not. It'll still run the same number of instructions and it'll take the same amount of time. But if the secret is 1, then obviously all the data in A and B are swapped. So what we can, let's see. Yeah, so actually I'll go more to the attack after this, but so what they need, first of all, from the attacker is that they need to know how to evict the A array. They also need to know how to monitor the data that the pointer points to. So they need to evict both of these lines from the from the victim's address space from the attacker. So previous work, they build off previous work that uses a high resolution timer via like a separate counting thread. So they spawn a thread that just count indefinitely, and they can use this to kind of simulate a high resolution timer, even though they don't have access to it because they have unprivileged code. They also need to generate their eviction sets in order to be able to evict all of the L2 that holds A and also holds the data the pointer points to. And they use a couple tricks, they use a couple tricks here. I'm not going to go too in depth, but in order to figure out that eviction set, there's some like tricks they can use to kind of narrow what their search space, and they can find it pretty easily once they narrow their search space. So now I'm going to go through a step-by-step of how this attack really works. So first, the attacker passes A filled with a bunch of dummy data and B filled with the pointer. Okay, and the pointer is every address in B. And then we enter on the victim side. We enter the CT swap, and A and B are going to be swapped only if the secret equals 1. So in the background, while this is running, the attacker thread is constantly evicting A from the cache using their eviction set A that they have found previously. But crucially, they're not evicting B. So they're constantly writing data into the cache in the same place that they know that the victim's A is going to be. So after the first loop, right, let's say A and B are swapped, right? That means that AI minus 1 now holds pointer because it was swapped from BI minus 1. Then on the next loop, and then after that, it's evicted from the cache by the attacker, right? Then on the next loop iteration here, right, we see delta equals AI XOR BI, right? So right there, we're loading AI back into the cache on the victim side, right? And once we load AI back into the cache, and so it's just recently evicted, it's considered a fresh load, right? And since this fresh load now contains the pointer that was just swapped in from B, DMP will activate. DMP will activate and prefetch the data that pointer points to. And so using the prime and probe on the attacker side, we can now check if that data has been prefetched or not by using a regular prime and probe attack on the same address where the data is supposed to be. So the real key detail here is that when the secret is 0, it's not swapped, right? And when it's not swapped, there will be no DMP prefetching because B is already in the cache. So it's not a fresh. You're not freshly bringing in B. You're only freshly bringing in A every iteration because you're evicting A with the background thread. And so this is basically what it looks like in the timing. So as we can see, when the secret is 1, it's higher latency for the prime and probe on the data that A writes to. And if not, obviously it's just lower latency. So it's pretty clear to see. We can tell pretty easily if the data was prefetched here.
Okay, so like their next, probably more unsettling contribution to this paper is that they actually take the exploit they developed and then bring it into battle with real world implementations of constant time cryptography. The paper tackles 4 implementations. In the interest of time, we'll only go over 1. In this case, we're going to be cracking Golang's RSA 2048 encryption. How it works is it basically exploits a property of the modular multiplication that RSA uses. You don't have to know exactly what the RSA algorithm does. TLDR, I just want you to focus on this line here. Just know that at some point in the decryption subroutine, there is this line that kind of plays the role of what I mentioned earlier, right? This is the line where we have that kind of mixing between a cryptographic secret, which is the prime number P in this case, and an attacker-controlled input, the ciphertext C, right? And if you recall from modular arithmetic, if C happens to be less than P, then C mod P will just be equal to C, right? So we kind of have like this, is 2 different outcomes of this intermediate value T naught. One of them is where T naught is just equal to C. Now this is important because C is a known value, right? It's an attacker-controlled ciphertext. So we're effectively giving the attacker a way to introduce a known value that we know will be checked by the DMP. So what the attackers did is that we can basically prepare pointers within this ciphertext payload, and then they do it such that the math works out, like the DMP restrictions all work out and the math works out such that if C is less than P, then C mod P just preserves the C value. And then when the DMP loads it, when it gets loaded from memory, the DMP will actually dereference these pointers, bring data into cache. And then from there, as you know, we can just use prime and probe to check cache latency and deduce whether this bit that we're currently guessing is actually 1 or 0. The authors demonstrated that you can do this for up to about 560 most significant bits of the secret key, up until the error rate of like guessing incorrectly starts becoming non-negligible. But that's fine, because then they could just take it, they could just finish the attack in some offline step, or they use another method to just get the remaining bits. So in total, you still crack the entire 1024 bits of the RSA secret key prime number P. Other implementations that we don't have time to go over is just they demonstrated that you can also extract the key from Diffie-Hellman, which is pretty a big deal, as you might be able to imagine. If you may not know, Diffie-Hellman is used in transport layer security, or TLS, so that's kind of a big deal. They also demonstrated that post-quantum cryptographic primitives like Kyber dilithium weren't actually safe from this vulnerability either. Just really quickly going over the evaluation methodology for all 4 of their demonstrated attacks. In principle, they're all about the same. They collected a bunch of prime and probe latency data points and then compared them to like a profile threshold. So like down here, these were like the numbers and the error ranges that they gave. As you can see, it's similar to that histogram that Jacob showed earlier, where it's pretty obvious like whether or not latency corresponds to a DMP activation or an unactivated outcome. They also measured the time it takes to kind of extract the key both in online phases and offline phases, kind of just demonstrate the feasibility, right? Speaking of, that brings us to our main results. So main takeaways of this paper is that as long as the DMP activation depends on some property of the secret, it doesn't matter if the cryptographic algorithm like is constant time in implementation, right? As long as there is some kind of dependence on the DMP activation and the secret, there is this opportunity for information leakage, which then effectively reduces the problem to a traditional cache side channel attack problem, right? Where we can just use prime and probe to check if the DMP was activated, and that in turn gives us information. As you recall from the threat model, this didn't require any elevated privileges, and the attack takes at most hours, maybe even minutes, so it just demonstrates that this could be a practical threat. The authors also close off by saying that after investigating other microarchitectures, they found that this is kind of inherent to the way we do hardware these days. So the problem isn't really tied to like a specific processor. It requires more hardware-based countermeasures.
Yeah, so there's some proposed countermeasures that the authors give. So of course, we can separate the actual code execution on separate cores. So we move it onto like an efficiency core that has no DMP. And then we won't, of course, the downside of that is the performance penalty. We can also like instrument the code to mask sensitive values. So this obviously changes like a lot of the code structure, and also we're going to have some sort of performance penalty because we're like just doing more instructions. There's also like ad hoc defenses. So like, you know, like we could fix this one issue, right, with like some specific fix, but it doesn't fix the whole idea of DMP in general. Like prefetching stuff that we don't just based off of information in that's brought into the cache. And of course, the one that they suggest is hardware and ISA extension support. So like that you could just disable DMP for sensitive areas of the code. Yeah, so we have a couple of discussion questions. I mean, we're kind of running out of time here, but I think one of the main ones is that OpenSSL dismissed the attack as like a local side channel attack when the researchers brought it up. And also the Go crypto team told them like, oh, this is low security. It's not really our problem. And like, do you agree or disagree with the fact that they say it's not really their problem?
I have a question.
Mm-hmm. Yeah, sure.
Sorry. The assumption, the threat model here is that the L2 is shared.
Yeah.
So does DMP, is there a reason why did they ever evaluate something that occurs on a larger share? My understanding is that with prime and probe, you don't normally do it on the larger L3 caches because it's difficult to find the entire L3 cache. And then when you do the probing of it, you get like, by the time you've probed the entire thing, the attacker is already gone to the next step. Sorry, the victim's gone to the next step. Did this paper ever mention any effect that DMP might have on like the larger L3?
No, they focused on the shared L2, private L1.
The threat model is mostly based on this threat model where you have like L1 private, L2 shared, and from there on.
So then does the attack stuff like trickles down if I just make my L2 private? Does that also like solve part of the issue?
Yeah, I mean, it's just if you solve the regular cache side channel.
No, I mean like not just regular side channel. So my concern is like whether DMP affects the cache state on the L3.
Oh. Yeah, they didn't talk about any L3.
Oh.
Okay. Yeah.
Thank you.
Thank you.
Good job, Victor. Thanks.
Sorry, I pronounced your name